So the second, let's talk about the case where the random variable z is a sum of the two random variable x plus y. And we're going to assume that the x and y's are independent. Otherwise, this problem is not tractable. So under the assumption that the two random variables are independent, the reason why we're looking at this case is that this is a very basic case, and also it has a lot of applications. In the real world, there are some cases where there's some random amount of the two or the multiple random quantities are added together, and we are wondering about what is the aggregate, the random quantity of those random variables. And for simplicity, let's assume that for the moment, these two random variables x and y can take a value of integers. All right. So we are interested in the distribution of z. Z is equal to the x plus y is equal to the z. So that's the probability that we are interested in. And that is, from the definition, we're going to take all combinations of the x comma y, where the x plus y is equal to z, and the joint PMF of x and y. Right? So take a summation of all these things. And then it turns out that this y is equal to the g minus x. So we will replace this y with the g minus x so that we only consider the summation in terms of x. Okay. Now, since the x and y's are independent, this probability is the product of the probability that x is equal to x and y is equal to the z minus x. And then and this is equal to the using the PMF notation, pxx and py z minus x. Okay, so here pzz is equal to the summation of all x, pxx and py z minus x. All right, this is a very special operations where the kind of z's PMF is some kind of combinations or the operations of the px and the py, and we call this pz is the convolution. So okay, of the PMF of x and y. So the convolution can be thought of some box where we have two inputs, px and py, and the pz. And this box consists of this operation. So in order to understand how the convolution works, we need to understand how this part works. Okay? So let's understand that. So if you look at this convolution equation, what we should do is that we can take the pxx first. For example, here we're looking at the example of px is given like that. We have only the value of the 1 and 4, the probability 1 over 3 and the 2 over 3. And this is the py. For three values of the minus 1 and 1 and 2, we have some probability mass. Okay? And first, we should be able to understand what this means. So in order to read, what we are doing is that we first flip horizontally the PMF of y. Because first, I want to compute the py minus x. So we should flip the py. And this is the flipping. Okay? So you see that 2 becomes minus 2. And 1 becomes minus 1. And minus 1 becomes 1. So it's flipped. So we have here and here and here. And then put it underneath the PMF of x. So here PMF of x is here. And flipped PMF of y is here. And then right shift the flipped PMF of by z. Okay, so we need to right shift by the amount of z. So here in this example, let's suppose that g is 3. This is 3. So essentially we are looking at the probability that g is equal to 3. So what we are doing is that we do the right shift of the amount of 3, and that is 1 is moved to the 4, and minus 1 is moved to the 2, and then minus 2 is moved to the 1. So we're doing the right shift. Okay, so we get this, And then what we can do is that we need to multiply the pxx and the pyz minus x. So this is a py 3 minus x in this example. So we need to multiply this and this. Okay, so if we do the multiplication, 4 and 4 here, and 1 and 1 here, and obviously for 2, this is 0. Okay, so the result is 0. So PG3 is equal to the 1 over 3 multiplied by the 3 over 6 plus 2 over 3 multiplied by 2 over 6. And that is PZ3. And we need to do this for all z. Like for example, what is PZ minus 1? What is PZ2? What is PZ4? The difference lies in the amount of the right shift, right? Here in this case, since the z is 3, we do the right shift by 3. But for example, like PZ2, then we have to do the right shift by 2. So right shift by the 2 is that 1 becomes 3. So like something like this, and this, and this. And we have to do the multiplication of the px and this right shifted version by 2. Okay? And through that, we can compute all the pz for all values of the z. Okay? So essentially, when you look at this convolution operation, what we are doing is to flip the PMF of y, right shift by the given amount of the z. When for example, z is small, like this. Okay? Now we move this shifted version of the PMF of the y just a little bit and do the multiplication, just a little bit and do the multiplication, shift a little bit and do the multiplication. And that's what we are doing. If you look at the continuous version of this, probably you understand better. Okay? So here in the summation is changed into the integral. Okay? Other parts are same thing. Since this is the integral, different from the discrete case where we do the summation of all possible values of x, here in this case, we need to compute the area. Okay? So for example, suppose that fx given like here and fy is given here. And what we have to do is that we first flip, okay? So we get this. And then z is given, so we do the right shift by the amount of the z. So this is minus c, and that becomes the z minus c. And this is minus d, and this is g minus d. So do the right shift. And do the multiplication of fxt and fyz minus t, and that's why we get this. All right? And then fz, z, is the area of this guy because it's the integral, this, and that's what the PDF for a given z. And using this we can compute pz minus 1, pz let's say 1, pz let's say 3, and everything and so on, right? Depending on how much we do the right shift. So essentially what we are doing is that we start from something like here and do the multiplication of this guy. Obviously this is 0 because the shifted version is located too far left. But we move here into like this and this. Oh, now we have some overlap. Okay, compute the area. Then it becomes the PDF value of the corresponding z. Okay, move here, do the multiplication, and the compute the area. Move here, and move here. That's what we are doing. That's what the convolution is. Okay. This example shows some kind of a convolution. The YouTube video, you can see there's some kind of animation. This is an FT and the GT. So FT convolution GT, where for GT, first do the flipping in terms of the horizontally, and then do the right shift by the amount of some number, and then do the multiplication and the compute area. So here, all right. So what it does is that we do the right shift of dotted blue rectangle, and then we have some overlapped area, and that is coming from the multiplication between the red guys and the dotted blue guys, and compute the area, and that's the value of the yt here in this case. When we do the right shift of the dotted rectangle, then the area increases, and that's why you can see this increases. Okay? Increase, and up to this point we get the maximum, and it stays at the same maximum value, and then we go down. Okay, that's what we can expect. Descent of the maximum, and the area goes down. As an example, suppose that two uniform random variables, okay, and what is the PDF of the z? This is almost the same as the previous animation, right? Because what we first do is, first we do the flipping, and then place here and move this to in the right direction. And if this is like this, then we have some overlapped area of here, and do the computation of the area, and then move a little bit, multiplication, compute the area, and then up to this point, like until we have exact match of the fx and the shifted version of y, that we get the maximum. Okay, so here the convolution or z, fz, is that starting from the 0, and we can increase, and in the 1 value we get the maximum, and it's go down just up to like this pattern, 0. Okay, so that's why we get this convolution result. If you think about this convolution, and the convolution is heavily used in the image processing, so you can see a very interesting example where the convolution is used in image processing. So for example, here we're looking at the scenario where the fx is just a series of the delta function. Delta function means that at some point we have just the mass. Okay, so integral of that one delta function is 1. Okay. Now hx is something like normal distributions. Okay. Now the question is that what happens if we do the convolution in f and h here? Then if you see that, what we need to do is that we first flip the hx. I think the hx is symmetric in terms of the y-axis. So the flipped version is the same thing. Now what we have to do is that we do the right shift. Now the right shift starts from the very small number. So the hx, the right shifted version of hx should be the very far left, and then do the multiplication. Probably we have some 0 thing, but move, multiplication, and the compute the area. Move to the multiplication and the compute the area. It turns out that we get this some kind of a multiple copied version of the hx, depending on the where we have some delta values of the fx. All right, because we have here in a delta function. Okay, so the convolution of the delta function point with some function x, that function is copied depending on the where the delta function is values. That's why if we do the convolution of this stock image with the sort of the lattice delta functions where this red point is the delta values, then what happens is this stock images is copied around these delta values, delta function values. That's why we get this. Similarly, in the left figure, when you see these images, so for example, this image has some point here. You see that the dots, okay? These all dots can be regarded as some delta functions at that point. Some kind of discrete values, okay? So if you do the convolution between these discrete delta values of each pixel images with this normal distributions PDF, and what we can see is that we have a very smooth images. Why is that? Because each pixel values, we have the smoothed version of the values, like because this is the kind of normal shaped the PDF. Okay, So if we do the convolution between this this thing and this continuous like normal distributions, then we get a very smoothed images. To go back to the sum of the two random variables, let's look at this very special case where the x and y's are normal random variable. All right. In the normal random variable, very unique result. Sum of the two normal random variables and also normal random variable. When the x is normal, then y is normal, and I have mentioned that this is a very unique property. Now I'm talking about the summation of the two normal random variables is still, this guy is normal, right? So generally, for the normal random variable, if we define the z is ax plus by plus c, where the x is normal and the y is normal, z is also normal. This is very convenient property because this normality is preserved under this all kinds of linear transformation. It's actually very convenient to come up with the closed form solution in many cases. Okay. I have just talked about the case of the two random variables. Then as you can see that we can extend this to some of the finitely many independent normal random variables. That's also normal, which is really good. How can we prove that? Do the integration very well. So this is a convolution, and the fxx is this PDF, and fyz minus x is this PDF, where z minus x is here. Okay, and since this is an fy, that we have expectation of y and the sigma, the standard variation sigma y, way up here. And do the multiplication and do the integration. Details of the integration is a little bit tedious, so if you have time, please do that, and then you end up having this thing. This is just a mathematical algebra, so I'm gonna go to the details, and we get this, and it turns out that this is a normal with the expectation is mu x plus mu y, and variance is sigma x squared plus sigma y squared. Okay.